All right, so group that worked on question 3. Let's talk first about part A, the average rate of change. How did you find the average rate of change between these two bond lengths, r equals 0.95, and these are measured in angstroms, and r equals 1.5 angstroms? So how did you find that average rate of change?
What we did was we took the 2 points that were given,
Mm-hmm.
so 0.95 and 1.5, and we just plotted them right on the x-axis as they were. And then you took those points and you would go up to where that point met with the line given on the y-axis to find the point used for the equation to find the slope. So for 0.95, on the y-axis, or for v, it would be 0.5. And for 1.5 on the x-axis, you had to go down to negative 0.5 or so for 0.1.
Negative 0.1? Okay.
Yeah, negative 0.1. So, and then you take the slope of that equation.
Exactly. So remember, average rate of change is a slope. And so if we want to know this average rate of change, we need the rise and we need the run. The run was more or less given, right, because we know exactly what are the values of r that these points have. So what was your run in this example? What was the denominator of your average rate of change? 0.55 angstroms. And then how about the rise? Negative 0.6. And that has the units of, what was it, kilogram angstrom squared per second squared. Okay. And so the average rate of change was what?
Negative 1.1.
So dV dr, average rate of change, was the rise over the run, negative 1 point.
Or negative 1.09, but we rounded it to 1.
All right, cool. Great. And the units of that are going to be, again, the units of the potential, kilogram angstrom squared per second squared, divided by the units of r, which are angstroms. So if you're going to simplify that, we can simplify it just by canceling an angstrom on top and bottom and making that kilogram angstroms per second squared. So that's for the average rate of change portion. Again, you had to use the graph in order to do this because you didn't have enough information from the formula to be able to find the vertical values, the v values, that corresponded to the two r values that you were given. But since you had a graph, you can approximate those values off the graph by finding those 2 points, as you did. How about part B? In part B, the question is, where on this graph would we observe the instantaneous rate of change to be 0?
So we said it was around the point where the x-axis would be like 1.1, and if you went all the way down the y, it was around negative 0.25.
Negative 0.25. And what is happening on the graph at that point that indicates the instantaneous rate of change might be 0?
It's the closest point on the graph that the line horizontal is at.
Aha! Horizontal is the key word there. We're looking for the point on the graph where the slope, remember that's the instantaneous rate of change, it's the slope of the graph. Even though the graph is curvy and not a straight line, we can still speak of its slope in an instantaneous sense. And so if the instantaneous rate of change is 0, that means that the slope of the graph at that point is 0. And what kinds of things have horizontal slope? I already spoiled the surprise. I said it in my head too fast. Having a slope of 0 means that a line is horizontal. Someone taught me that little trick the other day. Right? 0, horizontal, it's because horizontal has an O in it, and vertical does not. So don't screw up horizontal and vertical for that reason. So, by the way, from a scientific and a calculus perspective, this is interesting, because what have we really found here? We really found the minimum point, the minimum potential energy, from a physical sense, or the global minimum value, minus 0.25 of the function from a calculus perspective. How would we have done it? We would have just figured out where our derivative equals 0. That's all there is to it. But really, if you take a calculus course, the whole second half of your first semester is spent doing that. Finding where is the derivative equal to 0 and interpreting what happens at places where the tangent line is horizontal, as this one is.